So we're going to look at curve sketching today. We've been looking at finding where a function is increasing, decreasing, local max, local mins, and we just looked at finding inflection points and concavity intervals where our graph was concave up and concave down. And so let's first look at an example where we're actually given the information, we don't have to go find it, and put a graph together that has all the following properties. So let me just see if I can. I'm going to try to make a straight line. Okay, so let's make a x and y axis. And let's go in here and start picking out what they say. So for part A, it says it's continuous and differentiable for all real numbers. So we got to kind of think about what that means. There's no jumps in the graph. And if it's differentiable, that means there's no sharp corners. So it means it's smooth and continuous. Okay. So we'll remember that when we put everything together. Part B says f prime of x is greater than 0 on negative infinity to -3 and 1 to 4. So I'm going to put on here, let's just start putting our tick marks. So it's greater than 0. Derivative is greater than 0, then we know that it's increasing on these intervals. Okay, so from negative infinity to -3, we're going to be going upwards. I'm just going to put kind of a little note to myself that we're going upwards left to right. And then 1 to 4. Maybe just coloring this green because I used upwards as green. So 1. And I saw also from 1 to 4, we're also going upwards. Okay, so going to the next piece, f prime of x is less than 0 on -3 to 1 and 4 to infinity, which kind of makes sense if that was increasing. The other piece is probably decreasing. I guess it could be constant. It's decreasing. Okay, so now we're getting into concavity. Second derivative tells us if it's concave up or concave down. D says that our double derivative is less than 0 from negative infinity to -1 and 2 to infinity. So this is telling me that if it's less than 0, we talked about it, the kind of a parabola shape, depending on if it's increasing or decreasing, but it's facing downwards. And this is, where did it say? -1, negative infinity to -1. Okay, so we can kind of put this piece together, right? Because we know that it's in, well, I guess we might have to go back. But right now, I can see that it's increasing till I hit -3, and then it starts to decrease until I hit +1. But this is a concave down in here, and my guess is the other piece is going to be concave up. So I can see that at -1 that I have an inflection. So it's going to start to be concave up. And that's what this says right here. On -1 to +2, our double derivative is greater than 0, so it's concave up. It changes directions at 1. So concave up, at 1, we're going to have a min until we hit 2. And then this told me that it was concave down from 2 to infinity. So at 2, we're going to have another inflection point where it's going to change concavity, and it's going to be going downwards forever. And at 4, we're going to hit a max. Okay, so I put this together, but I need to make sure that the other pieces hold what I just drew. So let's go back and look at F. So F prime of -3, this is equal to F prime of 4, which is equal to 0. So if we have our derivative is equal to 0 at a value, we know we have a horizontal tangent line. So usually a max or a min occurs there, but not necessarily. So at -3, which I had said, we're going to have a max there, horizontal tangent line. And at 4, which I said we're also going to have a max there, we have a horizontal tangent line. Normally you wouldn't draw that, but I'm just showing. And then the last piece, G, says that the double prime of x equals 0 at the point -1, 3 and 2, 4. Okay, so this is where if our double derivative is equal to 0, we could have an inflection point. So this is where I'm going to be off a little bit. I had the right x values, but I don't think I put the right y values. So at -1, +3. Well, you know what we can do? So this is -1. We can go 1, 2, 3. Make that a 3 right there. And then at 2, 4. Okay, well, my 2, 4 is a little, my inflection point I had on the x-axis there. Okay, so this would be 4 up here and 2 is right here. So at 2, 4, I have to hit a point. So let me just kind of change my shape a little bit. Not really shape, but okay. So we have to come back down. We're concave up. We're concave up, concave up, concave up until we hit this point right here. And then we're going to be concave down now, and we're going to hit a point at 4. Doesn't matter, x is 4, but that's going to be a max. Concave down now forever. Okay, so there is one graph that holds all those properties. Okay, so we're not always given that information. We have to first go and find that information given a equation. So finding where our derivative was equal to 0, undefined, finding where it's increasing, decreasing, any max mins, concavity, finding double derivative equal to 0, undefined, and then inflection points, and then put it all together. So I'm pulling up curve sketching, so steps that you can follow to help you graph. So let's just walk through this really quickly, and you can find this in your textbook. And so I know that you guys are looking at your textbook through the MyMathLab program or MyLab and Mastering. So if you were trying to find that, you could find this on page 305. So let's go through curve sketching. So to sketch the graph of a function f, so first thing that we want to consider the domain of a function and note any restrictions. Okay, so recall domain are all the values you can have, your x values, your input that you can have, that when you plug it into the equation function, you're going to get back a real number. So usually look for trouble spots when you're finding your domain. And so that is, you're going to avoid dividing by 0. So you have to exclude anything that sets the denominator equal to 0. If you're taking a square root or any even root, we can't have a negative underneath that radical. A negative square root of -1 is I. It's an imaginary number. It's not real. So let me just read that again. So taking a square root or an even number of a negative number, we can't do that. or taking the logarithm of 0 or a negative number. So by definition, logarithms, it has to, that what you're taking the log of has to be positive. It can't equal 0 and it can't be negative. So if you see a logarithm in your equation, or if you see a radical, or if you see a fraction where you have variables in the denominator, we got to exclude those values, which give you problems. So that's probably the first thing that you want to do. Once you've done that, it's also helpful to find your y-intercepts if they exist. That's probably the easiest one to do for intercepts, y-intercepts. All you're doing is you're substituting x into your function f of x. You're substituting x equals 0 into your function f of x, wherever you see an x. To find x-intercepts, this is a little harder, or can be harder, but you're going to set your equation equal to 0. So set f of x equal to 0. And then hopefully it's not too difficult. Step 3, it depends. If you have a rational function, then remember we looked at vertical asymptotes. So finding our vertical asymptotes, if there are any. And recall that was where the denominator was equal to 0, but not also the numerator. So any value that set our denominator equal to 0, but not also our numerator, was a vertical asymptote. Then we also looked at finding horizontal asymptotes earlier in this course, where we were looking at the limits as x went to positive and negative infinity. So we wanted to see the end behaviors of our graph. Was it going to hit and follow a horizontal line somewhere, or was it going to shoot upwards or downwards as we go off to positive and negative infinity? The other thing, if you have an exponential function, find any horizontal asymptotes, and if it's a logarithmic function, then find any vertical asymptotes. So this is where I was just mentioning before I turned on the video that you may or may not have seen this before, where you use symmetry. So given a function, you would test to see if plugging in negative x wherever you see an x, if you get back the original function, then this tells you it's an even function, and even functions are symmetrical across the y-axis. So basically, if I had this piece right here and it was even, it would basically look like a parabola. It's symmetrical across this y-axis. If you folded the paper along that line, you get a mirror image. And so if you know half of your points, I mean, anything to the left of negative 0, then we would know what it would look like on the other side by mirror image. If you plug in negative x wherever you see an x and you get back negative f of x, so you get back a opposite y value, then the function's an odd function and it's symmetrical, but it's symmetrical across the origin. So that's where if you folded your paper in, let's say, quarters, it would be a mirror image. And so that's an odd function. So again, if you knew some points, you would know double what you had, because in this case, if xy was a point, then we would also have that negative x, negative y is a point. Where even if we have xy as a point, then we know that just changing the value of x but keeping y the same is also a point. So these are just tricks, but you don't need this piece to help you graph. And then this is what we've been doing the last week or so. So find your derivative. We're going to locate critical points by setting our derivative equal to 0 and determining where our function f prime of x does not exist, but does exist for the original. And that's where having our domain of the original is helpful. Find any relative extrema, determine where the function is increasing and decreasing. So seeing where it's increasing and decreasing, where our critical values are, we can tell if we have a max or a min. Once we've done that, we're going to take the second derivative. We're going to locate any possible inflection points by setting the second derivative equal to 0, and then determining where that second derivative doesn't exist, but does exist for original. And this tells us where it's concave up and concave down. We can then go through and plot our intercepts, our critical points, our inflection points, any asymptotes and points as needed, and take advantage of symmetry if we want. So once you've done that, you basically have all your points, you know basically what it's going to look like, and you can put it all together. So connect the points with a smooth curve using the correct concavity, being careful not to connect points where the function is not defined. You can always we've been using a little bit in this class, especially at the beginning, go to desmos.com just to check to see, does your graph look like the one that you graphed? Although you won't have that on an exam.
Professor, I have a question.
Yeah.
So on like considering the domain, like how would we find like the domain of like things that like aren't polynomial?
So when I look at the domain of things that are not polynomials, I look to see, is there going to be any value of x that's going to give me a trouble? Is going to give me something back that's undefined. So basically you have to look to see, are there any rational functions? So if there are any fractions where variables are in the denominator, then you're going to have to exclude things that set it equal to 0. Or if you have any square roots in your function, then we have to worry about negatives underneath that radical. The only other pieces that you have to worry about are logarithms. And then everything else, you should be okay. And we'll look at some examples like that. Leslie, where?
Okay, thank you.
You're welcome. Okay, so let's look at putting this all together. So in this case, let's say we have f of x is equal to okay, let me just start easier. I always want to jump into the harder ones, but I know I need to start easier. So let's just start with a polynomial at first. So how about 4x to the 4th minus 3x cubed minus 2x squared plus 6. And we want to graph this function. Actually, I'm in the wrong section, but we should be able to do this. Okay, let's just go ahead and do it. So let's graph this. We want to figure out where is it increasing and decreasing. The domain in this case, because it is a polynomial, our domain is all real numbers. So we don't have to worry about anything that excluding any values. We can write that as negative infinity to infinity. We want to take the derivative and find our critical numbers. So f prime of x. So derivative of 4x to the 4th is 16x cubed minus derivative of 3x cubed is 27x squared minus derivative of 2x squared is 4x. So now we want to find our critical numbers. Critical numbers are where our derivative equals 0 and where it's undefined. So this is defined everywhere, so we're okay there, but setting it equal to 0. So 16x cubed minus 27x squared minus 4x equals 0. So first thing I notice is that I can factor out a single x, and that would make it a quadratic factor. So x times 16x squared minus 27x minus 4 equals 0. And then I can see if I can use the AC method on factoring this, or I can just jump into using the quadratic formula. Those look like some big numbers in there, but that's probably what I would do, is jump in and use the quadratic formula. So quadratic formula, if you have a quadratic function, ax squared plus bx plus c equals 0, x is equal to opposite sign of the coefficient in front of x, so negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's do that on the side. So we're going to get x is equal to negative b. So negative of negative 27 is positive 27 plus or minus the square root of b squared. So negative 27 quantity squared minus 4 times our a value, which is 16, times our c value, which is negative 4. All over 2 times a, which was 16. So we get 27 plus or minus the square root. So I'm going to square negative 27, which is the same thing as 27 squared. And that's 729. Minus negative times a negative is positive, and we have 16 times 16. Because 4 times 4 is 16 times that 16. Just rewrote the order. So plus 256 all over 32. Plus 729. So the square root, this is 27 plus or minus the square root of 985 all over 32. So I'm just going to approximate, and we're going to get two numbers. So 27 plus the square root of 985, and then take that whole result and divide by 32. We get that is approximately 1.82 or 1.8. And if we did 27 minus the square root of 985, took that whole result and then divided it by 32, we would get negative 0.1. Okay, so those are our critical numbers. And we need to test to see where it's increasing and decreasing. Okay, so choose a number that's smaller than negative 0.1. So if you chose, how about x equals negative 1? And we're plugging this into our derivative. So f prime of negative 1, this is equal to negative 1 cubed, which is negative 1 times 16, negative 16. Negative 1 squared is positive 1 times that negative 27, so minus 27 plus 4. So again, we don't really care what this number gives us back. We just care is it positive or negative. And I can see right away that that's negative. And so I know it's decreasing on the left of negative 0.1. And so now check between negative 0.1 and 1.8. Well, I noticed that x equals 0 is in there. So if we went back in and we plugged in 0, actually that is a critical number too, guys, right? I forgot about this piece. Okay. So we got to test something in between negative 0.1, and it was really like negative 0.14 and 0. So how about negative 0.05? So we need to plug that back into the derivative. So this is where it would have probably been better if I chosen something that was inside the section we were in, because we're not getting, I guess we don't always get pretty numbers in mathematics. So So plugging that in, so I'm going to get negative 0.05. I'm going to cube that. Then I'm going to multiply that by 16. And then I'm going to take minus 27 times negative 0.05, and I'm going to square that. And then minus 4 times negative 0.05. I get a positive number if I do that. I get back 0.1305. So this is greater than 0. So it's increasing just a teeny tiny bit in that little area. So now choose something between 0 and 1.8. So how about x equals 1? So plugging it into the derivative, we want to see is that positive or negative. So I got 16 times 1 cubed, so 16, minus 27, minus 4. I can see that this is less than 0. And so this will be decreasing in here. And then 1.8. Anything bigger than 1.8. So how about x equals 4? And so plugging it into the derivative, f prime of 4. Well, 4 cubed is 64 times 16 minus 27 times 16, because 4 squared is 16, minus 4 times 4, which is 16. That gives us positive number, 576. So this is increasing. Let's just stop there in the fact that let's just say that this was asking us where it was increasing, decreasing, and then let's go to one that might not be as bad. So it's increasing. We saw from negative 0.1 to 0, about approximately, union 1.8 to infinity. And it's decreasing negative infinity to negative 0.1. And zero to 1.8. Okay, 3 times 3 is not 27. 3 cubed is 27. And up here, at the very beginning, when I was taking the derivative, I said 3 times 3 was 27. So you know what we're going to do, just because we can. We're changing this problem as this was a 9x cubed in there originally. So it might have come up a little nicer. Let's start a new problem. Okay. So same kind of directions. We want to graph this, but we didn't really graph that last one. So how about f of x is equal to x cubed minus 6x squared plus 12x minus 11. Okay, so again, polynomial, it's not going to have, it's differentiable everywhere. It's defined everywhere. We don't have to worry about the domain. So now take the derivative. And so derivative of x cubed is 3x squared minus the derivative of 6x squared is 12x plus the derivative of 12x is 12. And then the derivative of a constant is 0. So let's find when this is equal to 0. And at the same time, I'm going to pull out a 3. So that would give me 3 times the quantity x squared minus 4x plus 4 equals 0. I notice that this factors, there's two numbers that multiply to positive 4 and add to negative 4, which is negative 2 and negative 2. So we have 3 times the factor x minus 2 times the factor x minus 2 equals 0. So setting each piece equal to 0, well, 3 never equals 0. X minus 2 is equal to 0 when x is 2. I don't have to write this out twice. If you'd had college algebra, we would know that that multiplicity is even, and so it's just going to touch the x-axis. Actually, this is not. This is the derivative, so don't worry about that. Okay, so x equals 2 is our only critical number. And so we're going to put that on the number line, and we're going to test on the left and the right of that critical number. And so let's try x equals 0. Plugging it into the derivative, notice we get back our constant 12. So f prime of 0 is greater than 0. It's increasing. So choose a number now that is bigger than 2. So how about 3? If we plug in, 3 into the derivative, so f prime of 3, we get 3 squared is 9 times the 3 in front, so that's 27, minus 12 times 3, so that's 36, plus 12. 39 minus 36, that's going to be a positive number. So it's also increasing. So this function is strictly increasing. Now let's look at, and right here, we have got that was 0. So it's going to look something like this, where it levels out a little bit and then goes back up. But let's check and make sure what our concavity looks like. My guess is it's going to be concave down and then concave up. But let's look. So to find concavity, we want to look at the second derivative. So taking the second derivative, so f double prime of x, well, derivative of 3x squared, that's 6x. Derivative of negative 12x, so that's minus 12, and the derivative of 12 is 0. So we want to look at when this is equal to 0. Let's factor out a 6 while we're there. So pulling out a 6, we get x minus 2 equals 0. And so I can see that at x equals 2, that is also, looks like an inflection point. X equals 2. So let's check it. Choose something to the left. So how about x equals 0? Plugging it in, though, to the second derivative. So f double prime of 0 gives us back negative 12. So this is less than 0. It's concave down. If you want to kind of follow with what we know that it's increasing and it's concave down, then look at that piece of the parabola that is increasing concave down. That's going to look like the first half of that parabola. Now choose something that is to the right of 2. So how about x equals 3? And we're plugging it into the second derivative. So we have 6 times 3, which is 18. 18 minus 12, that's a positive number. It's bigger than 0. So this is concave up. It's concave up. So we have a parabola that kind of faces upwards. But notice from 2 on, it's always increasing. So again, we can kind of think about that shape. Increasing, but concave up. So we know we have a critical point and an inflection point at x equals 2. So we need to figure out what that value is. And we have to plug it back into the original equation to figure out what that point is. So let's look at what is f of 2. So f of 2, 2 cubed is 8, minus 6 times 2 squared. 2 squared is 4 times 6, so that's minus 24, plus 12 times 2, so 24, minus 11. So I noticed I had a negative 24 and a positive 24 cancels. 8 minus 11 is just negative 3. So we have a point at 2, negative 3. So we can put this all together now. And x is 2, y is negative 3. If we wanted to, we can find intercepts. So like right here, we could figure out that we have a y-intercept at negative 11. And we know that it's increasing concave down at first. Okay. Kind of looks like a straight line for mine. But concave down. And then it's going to change to concave up, but still increasing. If we could, but without any college algebra, I can't help you with how to find the x-intercepts of that function. I'm going to pull this up on Desmos and then let's compare the graph. So pulling up the example that we had just graphed on Desmos and graphing it on that function, you can see that this x equals 2, there's that horizontal tangent line, which we had found. That was also the place where it was changing concavity. So we had concave down and then concave up. And so we got the right picture. If you look at this, we can see that it crosses the x-axis about 3.442. Okay, so the next example is a rational function, which is negative 8, and that is all over the quantity x squared minus 6x minus 7. So looking at this function, I noticed that we have to worry about the domain because we have variables in the denominator. And so let's find out when the denominator is equal to 0, and we can do that by factoring. So we have negative 8 all over. So factoring that denominator, the two numbers that multiply to give us that constant negative 7 and add to give us that coefficient negative 6 is negative 7 and positive 1. So we can factor that as x minus 7, x plus 1. So for our domain, we can't have values which set our denominator equals 0. So for our domain, x cannot equal positive 7 and x cannot equal negative 1. Recall values which set the original function's denominator equal to 0, but not also the numerator. These were our vertical asymptotes. So we know that we have vertical asymptotes, I'm going to call it VA, at x equals 7 and x equals negative 1. Okay, so we need to go through. Also, we can find horizontal asymptote. Remember, we could look at the limit as x is going to positive and negative infinity. We can talk about if that changes. Of our function, negative 8, all over x squared minus 6x minus 7. Well, if you plug in positive or negative infinity wherever you see an x, you get -8 all over plus or minus infinity squared minus 6 times plus or minus infinity minus 7. So that denominator is growing and our numerator is staying the same. And so something small over something huge is going to go to 0. So we have a horizontal asymptote. I have y equals 0. So let's find our critical numbers. So we need to take the derivative of f of x. So we need to use the quotient rule. So f prime of x is equal to the derivative of our numerator. Well, the derivative of our numerator is just 0 times the denominator, x squared minus 6x minus 7. So I really don't have to write it there. Minus my numerator, so minus a -8. I could write +8 times the derivative of the denominator. So derivative of the denominator gives us 2x minus 6 all over this denominator quantity squared. X squared minus 6x minus 7 quantity squared. So let's distribute this +8 to the 2x minus 6. So that would give us 16x minus 8 times 6 is 48, minus 48 all over x squared minus 6x minus 7 quantity squared. Okay, so this is undefined. Same place where it was undefined before. If I factor that denominator, so it's undefined wherein x is 7 and x is -1. So it could change concavity there, but it also could change as an increasing, decreasing. But those are asymptotes, so that would not give us an inflection point or a max or min. But we do need to test on either side of that. And then we also need to find out, when is this derivative equal to 0? Really, all we're worried about, when is that numerator equal to 0? Because having the numerator equal to 0, 0 over a number is 0. I could think of this as multiplying both sides by that denominator. So 0 times the denominator is 0 equals the denominator times the right-hand side. That fraction goes away, leaving you with 16x minus 48. We can add 48 to both sides. So we get 16x equals positive 48. And then divide both sides by 16. We get x is 3. Okay, so looking at our critical numbers, we have 7, -1, and 3. So -1, 3, and 7. So we have 1, 2, 3, 4 different intervals that we have to test. So something that's smaller than -1. So let's think about it when we plug in here, really again, so the derivative, we are just worried, is it positive or negative? Notice that our denominator is quantity squared in here. So our denominator is always going to be positive. So let's say we plugged in x equals -2. So f prime of -2. Well, -2 times 16, that's negative, minus 48 is negative. So this is a negative number all over a positive number. So this is less than 0. So we know it's decreasing. So now choose a number in between -1 and 3. So how about x equals 0? So f prime of 0. Well, notice I get 16 times 0 is 0 minus 48. So my numerator staying negative all over my positive denominator, so this is less than 0. So this is decreasing. Choose a number between 3 and 7. So how about x equals 4? Plug it into the derivative. Only worried is it positive or negative. So 4 times 16, that's 64, minus 48. That's going to be positive in the numerator, positive in the denominator. This is greater than 0. It increases. Now choose something bigger than 7. So how about x equals 8? Same thing is going to happen when we plug in 8 into here. 16 times 8 is going to be bigger than negative 48. So we're going to get a positive number in the numerator, positive number in the denominator. This is greater than 0, so it's increasing. So we want to, now we know where it's increasing, decreasing. We need to figure out what the second derivative is to find concavity. So second derivative, I'm going to have to use quotient rule. So taking the derivative of 16x minus 18, that just gives me 16 times this whole denominator, x squared minus 6x minus 7, quantity squared, minus my numerator, 16x minus 48, all times the denominator, the derivative of the denominator. So we have to use that power rule, chain rule, bring our power down front, 2 of the inside, x squared minus 6x minus 7, times the derivative of that inside. Derivative of that inside is 2x minus 6. And this is all over x squared minus 6x minus 7 squared squared, so to the 4th. So it will help us if we first factor instead of just expanding out, because notice that denominator piece right here in the numerator when we brought it up, and this piece right in here, x squared minus 6x minus 7, those are the exact same thing. So we can factor one of those out of there. So we can pull one of those out, x squared minus 6x minus 7. We're going to pull one of those out. And then also notice that here we have a 16 and here we have a 2. So we can pull a 2 out of that also. So if we pull a 2 and an x squared minus 6x minus 7 out of that first kind of grouping, we're left with an 8, and we're left with 1 of the x squared minus 6x minus 7 factors. Then we have minus, we pulled this 2 out, we pulled this factor out, so all we're left with is this parentheses 16x minus 48, and this 2x minus 6. All over this denominator, x squared minus 6x minus 7 raised to the 4th power. So one of these is going to cancel in the numerator, or that's going to cancel in the numerator with one of them in the denominator. It might help us if we factored out an 8. You actually can factor out something bigger, or we can deal with bigger numbers. But notice here we have an 8 out front, and I see 16x minus 48. I could pull an 8 out of that. That would give me 2x minus 6. So if we pulled out these 8s, factor out an 8 there. It's just going to give us less that we have to deal with distributing, and we don't have to deal with as big as numbers. So we really have this 2 out front, all times that 8 that we were pulling out. And then we would be left with just the x squared minus 6x minus 7 minus, here we have to distribute 2x minus 6 times 2x minus 6. So boiling that out, 2x times 2x, that's 4x squared. 2x times negative 6, that's negative 12x. Negative 6 times 2, so minus 12x. And negative 6 times negative 6 is plus 36. All over the denominator, x squared minus 6x minus 7 quantity cubed. So we have 16 times the quantity. Here's going to be, we're going to have to distribute this negative sign. So really, we're going to have a x squared minus a 4x squared. So that's a negative 3x squared. We're going to have a minus 6x. And this is actually going to be plus 24x. Because negative 12x is negative 24x, but this negative that has to be distributed makes it positive 24. So 24x minus 6x, that's 18x. Plus 18x. Here we have this negative 1 times this 36, so that's negative 36, negative 36, and a negative 7, that's negative 43. All over x squared minus 6x minus 7 cubed. Okay, you have to find out when this equals to 0 and where it's undefined. So we're really only worried about when is that numerator equal to 0. Unfortunately, it doesn't look like it factors, but it could. And where it's undefined. So I would probably use the quadratic formula on that negative 3x squared plus 18x minus 43. So I would probably do some side work over here. Let's just bring it over here and look at finding out when that's 0. So x is negative b, negative 18, plus or minus the square root. If you square 18, we get 324. Minus 4. So I'm going to just do it right now. So negative 4 times a, which is negative 3, times c, which is negative 43. That gives us negative 516. We're going to have a problem because that gives me a negative underneath the radical. So there's no real number which is going to set this equal to 0. So no real solution. So really, we're only worried about where it's undefined. So it's undefined, same place it was undefined before when the denominator is 0. So when x was equal to 7 and -1. So on the number line, we would place those down. And we just want to test concavity, concave up or concave down. So we're plugging it into the second derivative. And we're seeing, is it positive or negative? So let's choose a number less than -1. So how about x equals -2? Plug it into the second derivative. And we want to see, is that going to be a positive number or a negative number? This one's a little harder to see because we have a cubic in the denominator. Okay, the denominator, if I plug in -2, it's going to be a positive number. In the denominator. If I plug in -2, that's going to give me negative. It's going to be a negative number in the numerator. So this is less than 0. We know it's concave down. Choose something in between -1 and 7. So how about x equals 0? Plug it in. If we plug in 0 in the numerator, notice we'll have this 16 out front times the -43. So that's a negative number in the numerator. 0 in the denominator, we'll have -7, and then we'll have it cubed. So that's negative. So negative over negative is positive. This is bigger than 0. This is concave up. And then a bigger number, so let's plug in 8. So x equals 8. Plug it into the second derivative. We want to see, is that positive or negative number? I can't tell by looking at it. So 8 squared is 64 times a -3 plus 18 times 8, and then a -43. I'm wondering if that's -91 times 16. So that's going to be a negative in the numerator. And the denominator, if we plug in 8 squared, so that's 64 minus 8 times 6, 48 minus 7. That's 9 cubed. And so that will be positive in the denominator. This is less than 0, so it's concave down. Okay, so we got a lot to now put together. We have all the pieces to put together so that we can graph this, or a lot of pieces that we can put together and graph. So let me pull all the information we need in one spot, and then we'll graph it. Okay, so let's put we put all the pieces together that we needed to graph this. And let's first put in our asymptotes. So we know that we have a vertical asymptote at x equals 7. So I'm going to draw a vertical dotted line to represent that. We also have a vertical asymptote at x equals -1. We have a horizontal asymptote on y equals 0, or our x-axis. Point-wise, I know that my y-intercept, I'm going to let x equals 0. So f of 0, notice I get -8 in the numerator all over -7. So 8/7, 1 1/7. I'm just estimating. So let's say that this was 1. So we're going to have a point about right here. So we know it's decreasing. It's never crossing the x-axis, and it's concave down. Well, if it's decreasing, I know it's not crossing the x-axis because there's no time when my numerator equals 0. There's no way that it could be above the x-axis. It'd have to be below the x-axis. So until -1, we're decreasing. And we're concave down. Decreasing concave down is going to look like this. So notice that that works if you're below the x-axis. You're going to be hugging your vertical and your horizontal asymptote. I know where this piece is. I know that it's decreasing and then increasing at 3. And it's concave up. So it's decreasing, concave up. Then at 3, we're going to increase. So notice that 3 was not a asymptote. So notice that you're going to have a min. When x equals 3. So let's plug that back into our original function to get a point. So f of 3, that's equal to -8 all over 3 squared. So that's 9 minus 6 times 3. That's 18 minus 7. So that's -8 all over 16, which is -1/2. Okay, so 3 -1/2, that's impossible. It's -16, which is +1/2. I knew that was impossible because it couldn't be crossing the x-axis, and I had already a point up here. Okay, so we have a min value there, and it's concave up the whole time between 1 and 7. So let me just kind of change my drawing a little bit, knowing that where this is. And then the last piece is increasing, and it's concave down. Again, increasing, I can't be below, I can't be above the x-axis. So it's like this. Increasing, but concave down looks like this. So we graphed our function based off calculus. So let me just pull up the graph really quickly, and then we'll take a break. So if you look at it, you can see that we got the exact same graph that never crossed the x-axis. It looked like a parabola shape in here. X equals 3 is where the minimum is going to be. Our horizontal and vertical asymptotes. Vertical at x equals -1, x equals 7. Horizontal asymptote at the x-axis.